Hello juniors, today we're going to be studying electronic assignment 30, which is transforming the reciprocal function. And basically what we're going to do is we're going to apply some of the transformations we have seen in chapter 1 and see how the reciprocal function behaves whenever we apply these different types of transformations. Okay, so the objectives for today's class are two. First, determine vertical and horizontal asymptotes, and then identify a rational function and its graph. So we're going to perform two different types of investigation here, and you'll be able to see how the different types of transformations affect reciprocal functions. So for the first investigation, it says, use your graphic display calculator to plot the graph of y equals 1 over x, which is the parent function of a reciprocal function, then y equals 1 over x plus 2, and y equals 1 over x minus 3. So we're going to start by doing that. I'm going to use Desmos. You can use your calculators if you want to follow this in order to plot these graphs. So I'm going to go to Desmos. The first one is 1 over x. That's the parent function. Then we had 1 over x plus 2 outside. And we have that blue function over there. And 1 over x minus 3 is the green function you can see over there. Okay, so I think you are already able to see what is happening, right? Let's stay first with the red one. Let's see. Use the plotted graph to copy and complete this table. So for each of these functions that we just plotted, we're going to identify the vertical asymptote, horizontal asymptote, domain, and range. Okay, so if you look at the graph for the first function, 1 over x, we're going to see that the vertical asymptote is the line x equals 0, right? The y-axis. And the horizontal asymptote is the x-axis, which is y equals 0, right? So that's the original parent function. So we can say that the vertical asymptote is at x equals 0. Remember the rule that we learned also during chapter 1. To find a vertical asymptote, we need to set the denominator to 0, right? And the value that makes the denominator 0 in this case is directly x equals 0. That's why the vertical asymptote is x equals 0. And the horizontal asymptote, if there is no vertical translation, so here you have like a plus 0, there's no vertical translation, then the horizontal asymptote remains as y equals 0, as you can see in the graph. So the domain, remember the domain is always related to the vertical asymptote, and the range is always related to the horizontal asymptote. So the domain would be x different from the vertical asymptote, which is 0, and the range is y different from 0, which is the horizontal asymptote. Okay? Now let's look at the second function, y over x plus 2. I'm going to erase this and plot this one. What do you see here? In this case, you see that the vertical asymptote is still x equals 0. I can trace that for you to see x equals 0. So you get that vertical purple line over there. And if I graph, what do you think the horizontal asymptote would be in this case? The horizontal asymptote seems to be y equals 2, right? So if I plot y equals 2, you see that there is a horizontal asymptote over there, a line that the function never touches, right? So those are the asymptotes. So let's go back. The vertical asymptote, we are still the same, x equals 0. Remember, the same rule, we set the denominator to 0, and the only value that makes the denominator 0 is x equals 0 in this case. And the horizontal asymptote, we see that it was moved 2 units up, right? So y equals 2 is my new horizontal asymptote. So you see that it is directly related to the vertical translation in this case. So the domain is x different from 0, and the range would be y different from 2 in this case. The function it touches all values or has all values except y equals 2. Finally, the third one. If you already notice a pattern, what we should get is a vertical translation 3 units down, right? So now the horizontal asymptote should be y equals -3. So let's see. I'm going to erase this. Let's plot the green one. There you go. So this is the third function. And as you can see, the vertical asymptote is still x equals 0. But now the horizontal asymptote would be y equals -3. There you go. Okay, so there is a vertical translation of the asymptote, which originally was at 0. Now it is at -3 because of this vertical translation. So, vertical asymptote, x equals 0. Horizontal, y equals -3 in this case. So the domain would be x different from the vertical asymptote, and the range y different from the vertical asymptote. Okay? So it says factual. When you transform the graph y equals 1 over x onto this and this, describe the transformation that maps the graph of y 1 over x onto this function. So in the first case, we're saying that we have a vertical translation 2 units up. And in the second case, we're having a vertical translation 3 units down. So 3 units down. This is this case. Okay, then it says, what happens to the horizontal asymptote? Can you justify why this is the case by considering what y tends towards x become very large? Okay, so what's happening is that the horizontal asymptote is moving according to the translations, right? So asymptote moves according so actually we're talking about horizontal asymptotes. So horizontal asymptotes move according to the translation, to the vertical translation. That means if we move 2 units up, the horizontal asymptote moves 2 units up. If we move 3 units down, the horizontal asymptote moves 3 units down. Okay, what is happening to the vertical asymptote? As we have seen, the vertical asymptote is always remaining the same in these cases. Later on, we're going to study the case where vertical asymptote also moves. So in this case, it stays the same. Why is that? Because there is no horizontal translation yet, okay? We're going to see that later on. So which axis does the graph now cross? What are the coordinates of the point where the graph crosses this axis? Can you use algebra to explain why the graph crosses the axis at this point? Okay, so if you take a look, let's see, for example, the third one, the one that we have already plotted. You see that now we are having here, or the graph is crossing the x-axis, right? Before, the parent function, the red one, when we erase this, we saw that this rational function didn't cross any of the axes, right? It didn't cross the y-axis, it didn't cross the x-axis because both were asymptotes. But now that we applied translations, we see that we're having an intersection in the x-axis, right? And how can we calculate that? Well, we need to, so let's answer this. It crosses the x-axis now. And how can we calculate the value where it crosses the x-axis? Using the property, right? If it crosses the x-axis, it means that y should equal 0, right? And if y is 0, let's use this third function here. If y is 0, then we're going to set the equation to 0. 0 equals 1 over x minus 3. And then if we solve for x, we're going to have, if we take the 3 to the other side, we're going to have 3 equals 1 over x. And then if we flip this x here and the 3 goes here, we're going to get that x equals 1/3. That means that this rational function is crossing the x-axis at the point 1/3, comma 0, right? And 1/3 is exactly, as you can see here, 0.33333 and so on, right? So that's how we can calculate the value of the intersection with the x-axis. Okay, so finally for number 4, it says, what are the asymptotes of a rational function of the form y equals p over x plus d? So if we generalize what we just saw, we're going to see that the vertical asymptote in this case is always equal to x equals 0, right? Because there is no horizontal translation. But the horizontal asymptote is varying depending on the vertical shift, right? So it is always y equals d, whatever the value of d is. And you see that we're not looking at this value of p over here. In this first investigation, we saw that the value of p is always 1, but it doesn't matter if it was a different value. It wouldn't affect the vertical and horizontal asymptote. Remember that that value of p is causing a vertical or horizontal stretch, but it is not moving the position of the rational function. It's just changing its shape a little bit. Okay, so I hope this is clear. Let's move on to our second investigation. Actually, it's a continuation of this investigation, just to see what happens when we apply horizontal transformations. So it says, use your graphic display calculator to plot the graph. So we're going to do the same thing. 1 over x, 1 over x plus 2, 1 over x minus 3, and 4 over x minus 3, and this one over here, 4 over 2x minus 3. So you see that these functions are practically the same as we had before, but now the plus 2 and the minus 3 are with the x instead of being separated from the x as we had in the previous investigation, right? That means that we're going to be having horizontal translations instead of vertical translations. So let me change that here. I'm going to erase all of this. So the next one would be 1 over x minus 2, x plus 2, I think it was. Let me see. Yes, x plus 2. Then we had 1 over x minus 3. There you go. Let me plot the original also. Then we had 4 over x minus 3. 4 divided by x minus 3. And finally, 4 over 2x minus 3. 4 over 2x minus 3. There. Okay, so let me erase all of this for a second. There you go. So we have the parent function as always, 1 over x. If we plot the second one, 1 over x plus 2, what do you notice? You notice that now there is a horizontal shift. That is that the vertical asymptote is not x equals 0 anymore, but rather x equals -2, right? If I draw the line x equals -2, you see that now that is the new vertical asymptote. If I change the color, let's do with a plotted line, orange. You see that the vertical asymptote at x is now at x equals -2 instead of being in the y-axis, which is x equals 0, right? So that's what we're having right now. If I plot the second one, this one, you see that now the vertical asymptote is at x equals 3, so we're moving 3 units to the right, and so on, okay? what happens if I plot the fourth function? You see that the vertical asymptote is still at x equals 3. Let me do that, x equals 3, there you go. But the function looks a little bit more like stretched compared to this one, right? Let me change the color of this one. Oh. If I change color, let's use orange. You see that? Let me erase the original. But if we compare these two functions, they have the same shape, but the shape changes a little bit, but the position is the same, and the vertical and horizontal asymptotes are also the same. Okay, so that's what we change if we compare function 3 with function 4. Then if we look at function 5, which is the last one, you see that where is the vertical asymptote in this case? The vertical asymptote should be at 1.5. So if I draw the line x equals 1.5, you see that we have the vertical asymptote right there, right? Let me erase this one. Okay, how did I find that? Easy, just setting the denominator to 0, which is what we're gonna see right now. Okay, so I hope this is clear. So, in the first case, 1 over x, the vertical asymptote is, if we set the denominator to 0, it's x equals 0 in this case. The horizontal asymptote is y equals 0. This is the original function, so this would be x different from 0, y different from 0. Then the second function, as we saw in the graph, we saw that the vertical asymptote actually moved 2 places to the left. But an easy way to remember this without having to graph is just setting the denominator to 0. If we set the denominator to 0, x plus 2 should equal 0, then we would get the vertical asymptote, which is x equals negative 2, right? So x equals negative 2 is the horizontal asymptote, is the vertical asymptote, while the horizontal asymptote is still remaining the same because there is no vertical shift, right? So y equals 0, and the domain is x different from negative 2, and y different from 0 is the range. If we look at the third case, we can do the same thing. We can set the denominator to 0. So the vertical asymptote would be x equals 3. X equals 3. The vertical is still y equals 0. Sorry, the horizontal is still y equals 0. Then the domain would be x different from 3, and the range y different from 0. Now in this case, you see that we have exactly the same as this, except that we have a 4 over here. But as we saw in the graph, the 4 is only causing a vertical stretch, right? It is not changing the position of the function, it is just changing its shape. So the vertical and horizontal asymptotes are exactly the same as the previous example. So this is x equals 3, y equals 0, x different from 3, and y different from 0. Finally, in the last case, if we want to find the vertical asymptote in this case, we're going to follow the same rule. We're going to set the denominator to 0. So we're going to write 2x minus 3 should equal 0. And then we're going to solve for x. And you'll see that we're going to have x equals 3 halves. And x equals 3 halves is the same as saying 1.5, which is what I showed you in this graph, right? There you can see 1.5. Okay. So, in this case, the vertical asymptote is x equals 3 halves. 3 halves. The vertical asymptote, the horizontal asymptote is still y equals 0 because there's no vertical shift like the ones we saw in the previous example. So the domain would be x different from 3 halves. 3 halves. And the range is y different from 0. Okay, then it says, when you transform the graph y equals 1 over x onto y equals p over cx plus d, describe the series of transformations that map the first graph to the second. Be careful about the order in which you perform transformations. So basically, the value of p is doing a vertical or horizontal stretch, actually a vertical stretch, and the values of cx plus d are the one of C and D actually are the ones that are determining where the horizontal asymptote would be, where the vertical asymptote would be, sorry. So let's say that P, the value of P causes a vertical stretch or compress. Stretch. All right, stretch only. And C and D are determining horizontal translation. And if you want to know the exact value of the horizontal translation, then we need to set the denominator to 0. So Cx plus D should equal 0. So we're going to get that x equals minus D over C. And this is the vertical asymptote, right? The equation of the vertical asymptote. Asymptote. So if you want to know, if you want to have like a formula to determine the vertical asymptote, just apply this, negative C over D, where C and D are these two letters over here. Okay? So that's part A. What happens to the horizontal asymptote? In this case, it remains the same, right? The horizontal asymptote is not changing. Stays the same because we're not having any vertical shift. Then what happens to the vertical asymptote? Can you use algebra to justify this in this case? Yes, this is exactly the algebra that we did. So in this case, it is changing. It is changing. And the value is found by setting the denominator to 0, right? Which is exactly what we did right here. Okay, which axis does this graph now cross? What are the coordinates of the point where the graph crosses this axis? Can you use algebra? Yes. So if we look at this case where we're changing the vertical asymptote, we're going to see that now here, for example, the graph is crossing the y-axis, right? In the previous example, it was crossing the x-axis. Now it is crossing the y-axis. So if it is crossing the y-axis, we're going to set the value of x to 0 in this case. So it crosses the y-axis in this case. And in order to find the value, we're gonna set the value of x to 0, right? That means that the graph crosses the y-axis. So for example, in the last one, we're gonna say that y equals 4 divided by 2 times x, where x is 0, minus 3. So if we solve this, we're going to get that y equals 4 divided by negative 3. And 4 divided by negative 3 is actually negative 1.333 and so on, right? Which is exactly the value we got here, right? 0, negative 1.3333. So the coordinates of the intersection with the y-axis would be 0, negative 1.333 and so on. Okay. So it says, using what you have learned about transformation of the graph y equals 1 over x, can you find the equation of the asymptotes of the function of this complete function and hence state the domain and range? Yes, we can, and we're going to see that here, actually. We know that the vertical asymptote would be found by setting the denominator to 0, and that the horizontal asymptote depends on this value of q, which is a vertical translation. That's what we learned. And the domain and range are directly related to the asymptotes, okay? So finally it says, describe the transformation that maps the graph y equals 1 over x onto the graph y equals k over x when k is greater than 0 and k is less than 0. As we have seen, when we change this value of k, we are having a vertical stretch or compress, right? Stretch or compress. If the value is greater than 0, that is a positive value, then we are Actually, when we're talking about when the value of k is positive, is when we're talking about this, right? Vertical stretch or compress. So let me write this here. When the value of k is positive, we're talking about a vertical stretch compress. And if the value of k is negative, we're also talking about a vertical stretch compress, but we're also adding a reflection. So vertical stretch compress, compress, and reflection, right? Remember when we had a negative value in front of the rational function, the quadrants switched, right? Instead of being in quadrant 1 and 3, we're being in quadrants 2 and 4. So that's why we're also having a reflection in that case. Okay, finally, to summarize this, it says reciprocal functions of the form y equals k plus d plus k over x plus d plus c, where k, c, and d are constant, will have a vertical asymptote with equation x equals negative d, because we're setting the denominator to 0, right? So it's x equals negative d, and a horizontal asymptote with equation y equals c, which is exactly this value over here. Okay, so that's the rule. The vertical asymptote is found by setting the denominator to 0, and the horizontal asymptote is found by looking at the value that causes a vertical shift, right? So here's a TOK question to think about. It says, when students see a familiar equation with a transformation, they will often get a gut feeling about what the function looks like. Respond to this question. Is intuition helpful or harmful in mathematics? Okay, so that's something just to think about. Okay, so that will be it for today's class. I don't want to make this too long. We still have to see a rule to sketch. Actually, this is very short. I'm going to do this quickly because it's short. Okay, so it says, sketching the graph of a function in the form f of x equals p over cx plus d plus q. So this is a general rule in order to quickly sketch these types of functions. So it says, in order to sketch the graph of a reciprocal function, you need to know two things. First, the equations of the horizontal and vertical asymptotes, which we already know how to find, as we did in the previous investigations. And number two, the coordinates of any points where the graph crosses the axis, which is also what we did in the investigation. So let's see it through this example. It says, A, sketch the function y equals 1 over x minus 2. Show any asymptotes not on the axis as dotted lines. Okay, so first of all, if the equation is y equals 1 over x over 2, I'm going to find the horizontal and vertical asymptote. So to find the vertical asymptote, we're going to set the denominator to 0. We're going to say that x minus 2 should equal 0. So the vertical asymptote is exactly at x equals 2, right? This would be the vertical asymptote. Then the horizontal asymptote, is found directly by observation. As there is no vertical shift, this is plus 0 over here, the value of the vertical asymptote is directly y equals 0. Okay, and that means that the domain would be x different from 2, and that the range is y different from 0. Okay, and what else do we have to find? If there is an intersection on the axis. Okay, if we have a vertical translation but not a horizontal translation in this case, then this graph should cross the y-axis. Yes, it should cross the y-axis. So it crosses the y-axis. If it crosses the y-axis, we're gonna set x equals 0, right? Because it is crossing the y-axis where the value of x is 0. So if we set x to 0, we're going to get y equals 1 divided by 0 minus 2. And then if we solve this, we're going to get that y equals negative 1/2, right? Which is negative 0.5. That means that the graph is crossing the y-axis at point 0, negative 0.5 or negative 1.5. Either way is fine. So with these pieces of information, with the asymptotes and the y-intercept, we can do a quick sketch of this. We're going to say that, okay, so I'm going to make a quick sketch of this. Y-axis, x-axis, x and y. So I'm going to identify, I am going to identify the asymptotes first. The vertical asymptote is at x equals 2. So with dotted lines, because the exercise has to mark as dotted lines, I'm going to mark the vertical asymptote at x equals 2. So I'm going to say that 2 is right here. So dotted lines to mark the vertical asymptote. The horizontal asymptote is at y equals 0, right? Which is the x-axis basically. So I don't need to mark that as asymptote. And I know that the graph should cross the y-axis at 0, negative 0.5, which I would assume is somewhere around here. Negative 0.5. So then I am able to sketch this function, and I'm just going to make a hyperbola over here, and a hyperbola which crosses 0.5 there and then it goes down, okay? And that would be it to sketch this function, okay? It must be translated to units to the right because of this shift over here. So if we state the domain and range, fine, it says right on the equation of the horizontal and vertical asymptotes. We already did that. It's this one, and this one. And we found the domain and range, which are these two values over here. So that's it. We finished the exercise, okay? So I hope this was clear enough for you. If not, please let me know. You're going to be practicing later on with some exercises. See you, juniors.